Yeah, so sorry about that. 6 minutes late. That's a record for us now. So yeah, the idea for today is, of course, we need to finish what we did last time. And I really wanted to start with something that's called the product topology. We'll see how things are going, because I really needed these 5 minutes that we lost to Zoom. So yeah, this is all stuff. So the idea for last time is I wanted to include some ideas and some definitions. So the idea is you have a set. Here, remember, you don't need to have a topology. Usually you do not for the first part of this statement. You have some collection of subsets of X. And we introduce this T of B. I'm not going to write it here again, but remember we had a global description and a local description. We proved these two are the same, are equivalent. And then when you have a topological space, so what I mean is X comes with a topology, we said that this B is a basis if the set T coincides with this T of B that we defined. Yes?
I just want to clarify, for the T sub B, the local was defined by, we choose X and we defined the ball around it, but the global was just defined by the union of balls, right?
Right. So this is kind of union, and this is very imprecisely neighborhood. So notice here, B is a basis for T. I want to emphasize that because I'm going to define something very similar after we're done with this proposition. So the proposition was, okay, we say that B is a basis for this topology is if T coincides with T of B. A topology. So that was the question we're trying to answer, and this is the proposition. So notice I'm doing 3.4. That means proposition 4 from lecture 3. So the setup here is we have a set, we have a collection of subsets, then this T of B is a topology if and only if two things. First one is you can cover X using elements in B in your math BBB. And the other one is this very local thing. Whenever you have two sets in your basis, something like this, you have two of those, and you take anything in the intersection, you can always cook up a third thing in your basis. So here's your B1, B2, here's your arbitrary X in the intersection. You should be able to cook up some basic set there. And we were trying to prove this. One direction was done. So this was last time. And now we need to prove this one. We need to prove this one. So let's go there. How do we prove such thing? So we need to assume 1 and 2. 1 and 2 over here. And we want to show T of B is a topology. So we need to verify 1, 2, and 3 for the topology axioms. So let's say 1 is just going to give us by 1, X is in T of B. Here I'm using the global description of T of B. If X is a union of things, then it's in T of B. And also, we say that the empty set by convention is always in T of B. It's always a union of things. So this is kind of by convention. So part 1 of the axioms, kind of for free. Part 2 of the axioms, we need to take a set of indices, let's call it lambda, and a collection, let's call them UIs in T of B for all I in our index set lambda. And what we want to show is the union of these UIs is also in T of B. And that's for free. If we use the global description, it's absolutely for free. Remember, T of B is union of things in B. So if each UI is a union of things in B, then the union of them is also union of things in B. So it's just for free. So this is free. This comes from free just using the global description of T of B. I don't want to write this, but what I should do is something like each UI is a union of things over some index. So I'll have an index set, which is itself depending on I. So I'll have like a collection of index sets, and I don't want to write that, but it's for free. So let's not focus too much on that. And now for part 3, we need to verify the intersection axiom of a topology. So we need to take, let's call these guys U and V in T of B. And we want to show the intersection is also in T of B. So I want to use the global, here I want to use, sorry, the local description of T of B. And notice, if U and B, instead of being in T of B, are just in V, then 2 is exactly what we want. If we want to show B1 intersects B2 is in B, is in T of B, sorry, that's exactly what we need to do. Yeah.
Just remember, third one, which is the intersection lemma. Why are we defining V? Because don't we want to do U1, U2, or it doesn't matter?
Yeah, it's notation, yeah. Okay, so let's write our things. Say U is union of some. Let me see what can I do with my notation. So let's write this guy as a union of some BIs over an index set I, and let's write B as a union of sets. I will use A, J over some index set J. And here, the BIs and the AJs are in B. So if I compute the intersection of that double union, so now when you do U intersects V, what you have is union over I's of UI's intersects union over J of BJ's. And this here is just going to be double union over IJ of BI intersects AJ. And now we are very safe. Because if we take any X here, it's going to live on one of these guys. And then I can cook up a B3 inside of that. So hence, given some X in U intersects V, what we actually have is that X is in some intersection. AI intersects BJ for some couple of index, some I and I. Maybe let's use H and L because I want to keep my variables. And now I can use my property 2. So by 2 circled 2, we have some, there exists some B in B with X in B inside the intersection. HI intersects BL, which is also a subset of U intersects V. Wait a second, please. Now we are done. By the local description, sorry. Description of T of V. Of T of V. This means what we want. This implies U intersect B is an element of T of B. And that's the end for. Yeah.
you describe why did we choose subscripts H and L again?
So what I'm saying is, this is your intersection. It's just this union over two indices. So if you take something here, by definition, if you're in the union of things, you need to live in one of them. And one of them, I'm using H and L to fix some indexes. And then, of course, this is a subset of this because this is the union over all of them. Yep.
In the first line of 3, you write U as a union of basis elements BI and B as a union of basis elements AJ. But then in the second line, you write U as a union of basis elements.
Oh, yeah, thank you. So for some reason, I corrected that over there. Yeah, this should be nice. Yeah, I don't know what happened there. Probably, yeah, thank you. Okay, are we okay? So that's the end of the preposition. So definition 1 for today is, in case we're in that situation, so let X be set, and let's take some B inside of the power set, so a collection of subsets. So what's going to happen is we say that B is a basis for a topology. So you could also say it's just a basis. Well, if 1 and 2, if it satisfies 1 and 2 from the proposition. And notice these two things are very similar. We say that B is a basis for a given topology if the topology coincides with T of B. But we say it is a basis for a topology. So this is what I'm defining, basis for a topology, if it satisfies 1 and 2. And then, of course, as a consequence of the proposition, then T of B, maybe let's say B is a basis for T of B. For the topology T of B. So examples, or maybe, yeah, I want to give like 2 examples. The first one is the standard here for the reals, maybe let's say in the reals or for the reals. So that should be my X. 1, I have B standard, which is going to be all open intervals. So here take A smaller than B. This is a basis for the standard topology. That's what we discussed last time. For the standard that we call TSTD. And 2, this is called PL, something you visited during homework. You can take semi-open intervals now.
Isn't that the lower?
Right. So you can see this thing is a basis for something because satisfies 1 and 2. 1 and 2, not for free. So as a consequence, a basis for something for a topology. And whatever it generates, it's called, so this topology, it's called the lower limit. And you also saw a third one on the homework assignment, like yeah, and the K topology. But something I want to notice here, note for these two guys here, when you do B1 intersects B2, this is always an element of B. So that's particularly easy because your B3 can always be taken just to be the intersection. You don't need to like cook up a different B3 for each X. You can just take the same thing. So it's always B or empty, let's say. So it's easy to verify these two guys are bases for something. Because the second part, which is usually the complicated one, where you need to cook up a B3 for each X, comes for free because the intersection is an element of your B. So for any X, and the intersection can take B3 to be the intersection itself, which in general is not going to be an element on B. It's just it just happens to be the case here. Okay, yeah.
I'll clarify something in notation.
Mhm.
So for the lower standard in the homework, it was introduced to us via a basis, so that's a little more confusing. But for example, the basic for the standard topology, the standard topology is defined as the open sets in R such that there exists a U open where epsilon is greater than 0, such that B of X epsilon is less than U, right? So this what B is the interval, right? So we write that as A plus epsilon B plus epsilon whatever, right? But in this case, B is just the B for standard is just the interval that we would apply the topology to. So then, yeah, so then this would be all of the unions of the B standards would then define the standard topology.
I have two comments. The first one is I don't understand the question. And the second one is I don't know if there is a question there.
The question is, what's the difference between how we're writing these bases and then the actual definition for the topology? Because it looks just similar to how we define the topology in general. So why even?
So last time so remember, to define the standard topology for the reals, we did something that at that moment was weird. But then I told you we're going to make that natural just because we're going to keep doing that. And if once you do that, a basis for the standard topology is here open balls centered at some X. But then I said last time, that's just any interval. This is not, every interval like this is X minus epsilon, comma X plus epsilon for some X, some epsilon. So these two things are just different ways of looking at the same thing.
So we define the topology using balls, the ball definition, and then this is just the basis to more thoroughly define what that means.
Right. It's just, so here I'm just recalling stuff. And here I'm telling you, you can see this satisfies 1 and 2. So it's going to be a basis for something. That something is called the lower limit. And then I'm telling you why these two things work very nicely, because when you do the intersection, it's always something in the set. So it's very easy. Otherwise, you need to cook up some B3. Here, you don't need to do that. Okay, so that was examples. Now I'm going to switch to subbases. Subbases the idea is very similar. So the idea is very similar for subbases. This is still section 13. So the thing is, these two conditions still kind of hard, mostly number 2. So kind of complicated. So it'll be nice if we could like cook up some B's with these two properties. And that's what we're trying to do with subbases. So let's start here just with a topological space. So this is definition 2 for today. Let's start with topological space, xt, be a topological space. And I'm going to start, so I'm like recreating that first definition that's up there. And let S to be, so this should be calligraphic S, a subset of the power set of X. So we say, very easy definition, that S is a subbasis for the given topology for T if T coincides with something that I'm going to introduce now. Coincides with T generated by this B of S. And I need to tell you what B of S is. Where B of S is going to be, I need to make to look very, very simple. So what I'm going to do here, B of S is just going to be things, so subsets of X, such that, well, that subset is just V1 intersects V2 intersects Vn. So a finite intersection of things in S, where Vi is in S for all I. So what I'm saying here is T equals T of B means every open or opens coincide with unions of things in Vs. So that will be unions, arbitrary unions of finite intersections of things in S. So what I'm saying here, yeah, T contains, or it's just T equals arbitrary unions or of finite intersections of elements in S. So here, generic open looks like, let's call it U. It's going to be an arbitrary union over some arbitrary index set, and then a finite intersection from, let's say, J from 1 to this n that could change with I. And then it's going to be like Bj B1 or Bj I or something like this. Yeah.
Can I say that the power set of X is always a topology on X, and that every topology on X happens to be a subbasis of the power set topology?
No. So different subsets will give you different topologies in principle. So for example, here. But it's absolutely true that the power set itself is going to be a subbasis for something. It's also going to be a basis for something. But the something is just a discrete topology. Everything is open. So we don't need basis and subbasis to describe that. But yeah, that's true. Yeah. Yeah, go for it. Yeah.
Where's the word like after the intersection for
Elements. Yeah, sorry. Sets in S. Yeah.
This is a really basic question. Can you redefine what topological space means? Is it just a space where we have topology?
Yeah, yeah. Okay, so I'm kind of using my notion for basis. Or I'm looking at the recording. Yep. So I want to note here a basis for T is also a subbasis for T. So we have examples just by using what we know for basis. But what I actually want to do, that's of course not that interesting. The question now that I need to introduce is question given a set. So I need to replicate that question up there, given a set X with no topology and a collection of subsets. When is this T of B of S a topology? Right? Absolutely natural question. Just keep doing what we're doing. So I want to keep proposition 3.4 over here, just for you to look at how complicated it was. So this is the answer for when is T of B a topology? So the answer is complicated, kind of. But now our new proposition is going to answer that question. So proposition 3 for today. So in the future, this will be proposition 4.3. If we have a set X, and we have a collection, sorry, I want S here, inside of the power set, so a collection of subsets of X. Then the proposition is telling you that S, let's say, P of PS is a topology if and only if very easy. You can just cover your set, like part 1 over there, with sets in the subbases. So you can pretty much always, if you take any collection of subsets, such that for each element in X, that X is an element of some subset, then you have a topology. So the proof here will be an exercise where you need to use that. So it's an exercise. Of course, use 3.4. So what you can do is you can verify 1 and 2 are always for free. And the definition here is, so I defined before, if you have a topological space, what's a subbasis for that topological space, for that topology? But if you don't have a topological space, if you just have a set, so let X be a set, and let S be a subset of power set, collection of subsets of X, we're going to say it's a subbasis for some topology. So we say, oops, I forgot to redirect cameras. There we go. So we say that S is a subbasis for something. For some topology. Of course, when it satisfies this very easy property. If X is the union of the sets in S. And of course, in this case, S is a subbasis for T of B of S. Nothing else. Yeah.
You would put like this, I think I get the general idea, but a subbasis is essentially we have a basis, and then we're taking.
No, you don't have a basis.
Is that all B transaction?
B of S is a family of subsets that you can cook up using things in S.
Family of subsets of the intersections of the open set U, right?
Mm-hmm.
Okay.
So this you can define just using S. You don't need a topology. That's what I mean.
Subbasis is essentially a group of the intersections of an open.
B of S is the collection of finite intersections of things in S.
And then the basis.
And then the basis is going to be unions of things in BS, which means unions of finite intersections of things in S.
Yeah, all S is just a sub group of, or sorry, a subset of the power.
Yeah, yeah. Okay, so probably I could say that. And in this case, S is a subbasis. I'm saying for a topology, but that topology is going to be T of B of S. Couldn't be anything else. Okay, any questions? So of course, to prove 4, you just need to verify 1 and 2. Or use 1 and 2. Sorry, prove proposition 3.
Okay, to clarify, to prove proposition 3, we have to use 3.4, which was a way of proving that the bases are small. Where's that? Yeah. Prove the T of B is small.
So I don't want to give you too much examples because that's something you will have to do at some point. And I also want to cook up some general ideas using this sub-basis business, but at least I want to say something here. This is probably not the most interesting example we could do. But say again, in the real numbers, we could take S to be sets of these 4. Semi-open intervals where A is a real number. Maybe I want to use B here, or the other kind of open interval you could have. So I'm just taking infinite open lines. So here, when you do intersections of things in S, you have your intervals. So here, B of S, when you start doing finite intersections, to be honest, at most 2, what you'll have is just AB, subsets of R. But here I want to say A can be a real number, can also be infinite, and same for B. Or well, plus minus. If you want to cook up any of these sets, you can intersect these 2 guys. And that's all you could have when you start doing intersections.
Is that true if and only if B is greater than A? Otherwise, you have an empty set.
Right, yeah. Let's say if you allow A to be bigger than B, you have empty here. Yeah. But again, here by convention, the empty set should be here. Because it's like the empty intersection, which is kind of finite. So, okay, so that's one example how to use subbases. And probably at this moment, you might be wondering, well, is that business really useful? And hopefully I will convince you when we start doing more interesting stuff. The main issue here is, at the present moment, we're mostly defining topologies and doing not so complicated things with them. But we're lacking something that's very deep and also very general. When you do what we're doing in this class, namely you study sets with an extra structure, in this case a topology, you need to consider functions that preserve that structure. Otherwise, the theory is not going to be that deep. You can compare topologies with the definition we introduced last time, like finer and coarser than, but that's not really what you need to do. because you are not allowing yourself to go out of just one topological space. So we'll get there probably next week. And what I want to do now is, what happened here? Huh. Okay, let me fix this real quick. There we go. I have to use these notes. So I want to do the product topology now. So this is new part of the textbook, the product topology. This will be section 15. And also 22, but mostly 15. So the idea here is you have two sets. You know how to form the Cartesian product. You have two topological space. What can we do about the Cartesian product of them? So maybe let's remember some definitions. This will be kind of definition 5, thank you, for today. So my notes froze, so I'm using something else here. Definition 5. Let's take a finite collection of sets, x1, xn sets. Then for this family of sets, we define x1 cross x2 cross xn. Maybe x and cross are too similar. We define this set, the Cartesian product, as the family of n tuples. So a1, a2, blah, 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 an, where each ai belongs to the corresponding I. ai is in xi for all i's. So this is not new. And I want to actually tell you something new. So what's going on here? Why do we use indices here? Why do we say A1, A2, AN? Yeah. Right. But what I'm doing when I say A1? Maybe a hint I could give you. What if I call this guy A? The entire collection, I call it A. I'm telling you what's the one component of A, the two component of A, the nth component of A. So this A, what's actually doing, it is a function going from 1 through n. Do you see that? A is just a function. That's why I tell you A1, blah, 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 AN. And let's say it lands in the union of these xi's. Because I don't really know where it's going to land, such that this condition, A of I is in xi. Yeah.
Is this saying that A1 through AN are from the Cartesian product of all the sets?
This is one element of the Cartesian product. So one element is an n tuple. Now I'm trying to decide what an n tuple is. An n tuple is the function. The domain is going to be the index set, and the codomain was the union of the xi's, something like that. And what I'm doing this, because now I can go from this finite family of sets labeled by this thing to an arbitrary family of sets labeled by anything. I can define the Cartesian product of anything. Yeah.
Why is it like the union of xi instead of just like?
Oh, because I cannot just write 1 here. If I'm going to make AI live to the corresponding xi. So A1 lives in x1, A2 in x2, A3 in x3. So in particular, I need all these guys here. So I'm just putting the union there. But usually what you do is like you have a universal set and you put that universal set. You don't really need the union.
I kind of get what you're saying about the functions, but, well, so essentially, like, each A is a function, and each function represents like.
Each function represents a tuple. What I'm saying is a tuple is a function with n variables. Value on first entry is the first.
So the function A represents A1, A2, A3.
Right, these two things are the same. A tuple is the same as a function with this. And this condition is just this condition. But the good thing is now I don't need a finite index set here. So more in general, if we have, so let's erase this. In general, if we have a collection of sets, xi, where I is some index set, so this is a collection labeled by lambda, which could be anything. We define the product. Of course, now I cannot write all of them. So I'm going to use big product, big pi, over index set in lambda of my sets xi. Instead of collection of tuples, I have no way of ordering lambda, but I can always take functions. So it's going to be all functions, which let's use A, why not? All functions from the index set to the union of the xi's, but not all functions. I want them A of I. I want that to be an element in the corresponding xi. And somehow you should be convinced that when the set is finite, these two things are exactly the same thing. When lambda is 1 through n, these two things are the same thing. So I will write that. Hopefully you'll be convinced. But what I said before, note if you take lambda to be a finite set, 1 through n, then when you do the product of xi's over this lambda, let's write what lambda is, 1 through n, this coincides with x1 cross x2 cross xn. Are we okay? Do you have any questions? Yeah.
So your product topology, does that mean arbitrary Cartesian products of sets are topologies?
Well, now I need to define that. So far, I only have the definition for sets. And I think this is new for you, or most of you. Like an arbitrary product of sets is not a very common thing, but it's for topological reasons, it's very convenient. Now I need to address that issue. Like I need to go topological now. Yeah.
I kind of get it, because like, it makes sense that if you have a finite indexing set and you take the product, then it's gonna be the same as just taking the Cartesian product, but what would happen if it's infinite? Like, because I would think it could theoretically.
Well, if it's infinite, it's a new thing. That's what I'm defining.
But they're still equivalent, right?
When they're finite, they're equivalent. That's what I'm saying. Yeah. But hopefully you should realize we only use this notation because we have finitely many, so it makes sense for us to try to write them all the coordinates. But for a function, well, that's just the same thing. Function, you don't write all the values, you just know there is a function. Here what they're doing is you're writing down all the values of the function. Okay. So here we go topological now. So I want to say two things. I'm going to define two topologies. One of them is going to be very natural, the other one not so really, at this point probably. But I promise you I will convince you with functions at some point next week. So definition. Now I will start with topological spaces. So let's take a collection of sets that xi, where I is some index, be a collection of sets. But now I want them to be topological spaces. Not just sets. What I'm going to define now is the box basis. This is what I'm defining. Is this family. Is the collection P prime. Here what I'm going to put is products over indices of UIs. So this is going to be a subset of products of all xi's, where UI inside of xi is open for all I in lambda. So open according to the topology of xi. Yeah.
When we say the xi's are each xi is a topological space, does that mean there is a set x and a set yi and a topology ti for each of the xi?
Well, something like this. Maybe I can write that. So instead of saying this, I can say xi comma ti. So each ti is a topology on xi. And here, instead of saying ui is open in xi, what I should say here is ui lives in ti. That's what that means. Yeah.
I know I asked this question before, but I think I'm starting to get it. A topological space is just defined by the set and the topology. So here, if you want to say it's a topological space, you've defined the set and then you define the basis for topology. And that's what the box basis is.
So far, that's a good question, but going into the future. So far, this is just a collection of subsets. So this is a collection of subsets. So this is inside, don't have enough space. This is a collection of subsets for the arbitrary product. So to be completely honest, what's going on here is I really like this guy to be a topology, but it's not. That's kind of the problem. So what's the picture here kind of? The picture is something like, let's do two of them. You have an open here. You have an open here.
When you say you want the box basis to be a topology, do you mean you want it to be the basis of the topology, or you want it?
Well, it's always going to be a basis, but I will like this thing. So what I'm calling the box basis, this thing, I would really like this for this. I would really like this thing to be a topology on the product side, but it's not. And this is the example. So it's like you take reals here, and you do the product of two open intervals. You will have like an open square, right? But now we know if that's going to be open, then the union also should be open, right? So we want to have different squares. So maybe I want to have this square here. And I cannot just land these things using this idea. Because here what I'm doing, for example, this should be open, but to land this guy, I need to have this interval here, and I also need to have this interval here. But then that's forcing extra intervals that you don't want. So for example, that's forcing this guy. So why do I need to have both? Maybe I don't want to have both. Do you see what I mean? Do you want to say that again? So if I just want this guy, that's okay. But if I want these two guys, I need to consider these two guys. Now, also I need this guy and this guy. And just these two guys are forcing me to include this guy. And probably I didn't want that one. So this is not a topology. It's just not a topology. I need to consider unions of squares. Okay, so that's pretty much the idea of what's going on here. How are we doing with time? Have 4 minutes. So yeah, let's try to do this. So I want to show this its basis, essentially, because that's the important thing. Okay, let's prove its basis for some topology. And of course, I'm going to use proposition 3.4. Yeah, I didn't really prove it because, but you could. So lemma 6, this B prime is a basis for a topology on this arbitrary product. So the proof here will be I need to show 3 axioms for a topology. Maybe let's say the empty set. Sorry. Proof, we want to use proposition 3.4. So I need to verify 2 parts. The first part is the arbitrary product here, the arbitrary product of these xi's can be written as a union of things in B, and that's for free. So this guy is in T of B because xi is in Ti for each I. So what's actually going on here is that this guy is just in B prime. So I don't need to verify it's a union of things in B, it's just an element in B. And the second one, yeah, sorry, I don't have time, but what I will say is this follows from the following. What we need to do is we need to take 2 elements in B, given a product of UIs and product of BIs in B prime in the box basis. What we need to do is we need to take an arbitrary element of this intersection. UI intersects BI. Right? We need to take an arbitrary X here and show there is some third element in the basis topology. But this set is just the product of UI intersects BI. Just from this thing, if you take an arbitrary X here, it's here, so you can just use the definition. And I'm out of time. I don't want to keep you for long, so let's stop here. Probably we'll revisit this next time.